All right, welcome to the second lesson of the Earth Science portion of our class. And for this lesson, we're going to be looking at the idea of seeing the Earth as a system. So how can we use the concept of a system to organize the way that we understand all of the different processes that are going on our Earth? So our goals for this lecture are first to understand this concept of what a system is and apply that to the Earth. Then we're going to look at two very important systems that are going to sort of be referred back to as we continue on in our Earth science lessons. So we're going to first look up the hydrological cycle as the first system that we go into in more depth, and then the second one that we'll go into in more depth is the carbon cycle. So those are two very important systems that are part of our Earth. So to start out with talking about what we mean when we talk about systems in an earth science context. So a system is simply a set of interacting parts. So you've got different parts and they interact with each other in some way. They influence each other. They affect the state that other parts of that system are in. And we often differentiate closed versus open systems. So a closed system is a system that has no external interactions. That system is entirely working on its own. It's not influenced by anything outside of the system. An open system is influenced by some sort of external factors. And all of our systems on the Earth are open systems. Any system that we define is interacting with other things. And one of the big ways that systems on the Earth are open is they're open to solar energy. We're going to talk a lot in the Earth science portion of this class about the role of solar energy in shaping what happens on the Earth. So if we have a system that we're defining as parts of the Earth, it's receiving that solar energy from outside of that system. And any system can be made up of subsystems. So you can take one big system and you can break it down and look at subsystems that are happening within it. And all those subsystems are going to be open because they interact with each other to make up that larger system. So the Earth as a whole is a system, but then we can break the Earth down and look at subsystems that make up the Earth. And some of the major systems that make up our Earth, things like the hydrological cycle, the carbon cycle that we're going to be looking at in this lesson, are important because they link together these major parts of the Earth. So we often talk about the Earth as being made up of the different spheres. And so the picture there gives you a look at some of these spheres. So we have the lithosphere, or sometimes called the geosphere. That's the solid portion of our Earth, like the rock. Then we have the atmosphere, this envelope of air, of gases that surround our planet. We've got the hydrosphere, which is made up of all the water on Earth. We've got the cryosphere, which is all the frozen parts of the Earth. And the biosphere, everything that's living on the Earth. And these different spheres are linked together by different sorts of interactions that make up these important systems that we're going to be looking at. So when we analyze systems, one useful way to do it is to think of them in terms of stocks and flows. Because as the different parts of a system are interacting, that usually involves the exchange of materials, energy, and or information, right? Something's moving from one part of the system to another, and that's what that interaction consists of. So then we can conceptualize that system as a set of stocks, which are parts of the system where that material, energy, or information is present, and then flows, which are the movements of that materials, energy, or information from one stock to another. And so as an example here, we've got a bathtub. It's a very simple model of a system. It's got one stock, the amount of water in the bathtub, and then it's got an inflow and an outflow. So there's a flow into our bathtub from the faucet. There's an outflow from our bathtub through the drain. And of course, the bathtub system is an open system that's part of a larger system that is the entire plumbing network of your house, right? So that inflow to the bathroom is originating from another stock. It's originating from the stock of water that's found in your hot water heater. And the outflow is going perhaps into your septic tank. So that's another stock, right? Water is found in the septic tank as part of that larger system of plumbing that makes up your entire house. And then, of course, you're linked into an even larger system depending on where you're getting that water from. So if you are getting it from a well, right, the groundwater that you're drawing in from that well is another stock as part of this larger system of water. Or if you're hooked up to a municipal water line in a city or town, right, there's another stock, maybe in a water tower somewhere. And then you've got these flows linking these different stocks, moving water from one place in the system to another. And when we look at a system like this, we're often interested in whether that system is in balance. And so a balanced system is one where the total inflows and total outflows to each stock are equal to each other. So if we think about our bathtub, that would mean that the amount of water coming out of the faucet over a certain length of time, right, the amount of gallons per minute that are coming out of the faucet are equal to the gallons per minute that are draining out through the drain. So you're adding the same amount of water to the tub over a given period of time as you are taking out of it. And so this is a case where you have just one inflow, one outflow. But sometimes you have to add multiple inflows or outflows. So if your outflows are the drain and then also the water that you are splashing out onto the floor because you're a child playing in the tub, right, that splashing is another outflow that you would have to consider. You'd have to add together the splashing outflow and the drain outflow to get the total outflow from that stock that's in the tub to determine whether the tub is in balance. So if the system is in balance, so if those inflows are equal to the outflows, then the amount in that stock will not change. If your amount of water coming in through the faucet is equal to the amount going out through the drain, your water level in the tub remains the same. And that might be a high water level. If your water level got really high before you achieved that balance, it might be a really low water level. If didn't have much water in the tub at the time you achieved that balance, it could be anywhere up or down there, but as long as the inflows are equal to the outflows, you have balance in that system. If one of those is greater than the other, then your stock is imbalanced and it's going to rise or it's going to fall over time. So if your faucet is putting more water in than your drain's taking out, your tub is going to fill and it's going to rise until it reaches whatever its maximum is. It reaches the height of the tub. If your outflow is greater than your inflow, the tub is going to drain and that stock is going to fall until it hits zero if you don't make any further changes to those inflows or outflows. So a system that's in balance will experience no change over the long run in the amount of the material, energy, information, whatever it is, that's present in each stock. So let's look at a fairly simple model of a system. So we're looking here at the hydrologic cycle. So this is a cycle of water moving around our Earth. And so in the most basic sense, we can say there are three major stocks that we might note for our hydrologic cycle. Three major places that we're seeing water in our environment. So we've got some water that is surface water. We've got water in rivers and ponds and oceans and everything, sitting on the surface of the Earth. Then we've also got some water that's in the form of water vapor, right? We've got water that has evaporated into the air, that constitutes the humidity that's in the air. So that's another stock of water, right? That's a place where water is found. And then we've got clouds. So clouds are water that has gone up high in the atmosphere and then recondensed, right? Clouds are made out of droplets of liquid water that are floating up in the air because they're so small that air currents can keep them aloft. So we've got water in those three places, right? We've got surface water, we've got water vapor, we've got clouds, and then we've got flows connecting them. Okay, so we've got a flow from the clouds to the surface water in the form of precipitation. When those clouds drop that water as rain or snow, That's a flow taking water from the clouds into the surface water because it falls down to the earth. Then we've got a flow taking surface water into the form of water vapor through evaporation. As water evaporates off the earth, it becomes water vapor. It shifts from the surface water stock to the water vapor stock. And then we've got condensation closing the loop. So that water vapor that's in the atmosphere can condense back out into liquid form in little droplets that form our clouds. All right, so we've got these three stocks and we've got flows connecting them. And the balance among those will depend on whether the flow into one of those stocks is greater than or equal to or less than the flow out of those stocks. And of course, over time, that balance shifts. Right? Sometimes we have a much bigger flow into our surface water than is leaving it. If we've got a big rainstorm and so not much is evaporating, but lots of precipitation is falling, and so that surface water stock increases, it rises. We might get flooding. And then sometimes it goes the opposite way. If we have little to no precipitation, so our inflow to the surface water is very, very small, but we've got a lot of evaporation. Maybe it's a very hot, dry day, and so lots of that surface water is lost to evaporation, and our surface water levels drop. Right? So we've got that kind of very basic system going on. But of course, you'll have noticed that on this slide, I've got two other stocks hanging out there. We've got the biosphere and we've got groundwater. Right? Two other places that water can be found. There's water in the biosphere. Right? Every living thing has water in its body. And so that's another stock of water. It's another place that water can be found. And then we've got groundwater. We've got water that is underneath the ground, that is found in geological formations below the surface. And so we can add some flows connecting those other stocks into our hydrologic cycle. We can make our diagram a little more complex and therefore a little closer to reality. Right? So we've got flows from the clouds into the groundwater and the biosphere. Because as that precipitation comes down, right, some of it filters down into the groundwater rather than join the surface water. Some of it is absorbed by our biosphere. Of course, the biosphere can take water from the surface water and groundwater as well. Right? If you are an animal and you go down to the pond and get a drink, right, you are initiating a flow from the surface water stock to the biosphere stock by doing that. If you are a person that drills a well and gets drinking water out of the groundwater, you are initiating a flow from the groundwater stock to the biosphere stock. Then the biosphere can lose that water through transpiration, which basically means that as you are doing the processes that enable you to photosynthesize as a plant, that gives off water vapor. So that's one way that water flows from the biosphere stock into the water vapor stock. You've also got evaporation from like sweat and from animals and various other ways, right, that flow may occur. There's seepage of groundwater out onto the surface. There's infiltration of surface water into the groundwater. So we got a bunch more of these flows connecting this hydrologic cycle together. And so if we want to see if this is balanced in the long run, we would need to add up all of these flows, right? All of the inflows, all of the outflows to each stock and see if in the long run, the inflows are equal to the outflows. So we can make this picture even more complicated. So this is the hydrologic cycle diagram that was recently put out by the U.S. Geological Survey. So that is the federal department that gathers data about earth science for the United States. And on this diagram, they use the terminology of pools and fluxes. That's just alternate terminology for what I've been calling stocks and flows. So depending on where you look, you'll sometimes see stocks and flows as the terminology. You'll sometimes see pools and fluxes. It refers to the same thing, right? A pool is a stock, is a place in the environment where, in this case, water can be found. A flux is a flow. It's the movement of water from one pool / stock to another. And so you can see that this diagram has added a whole bunch more stocks and flows or pools and fluxes in their terminology to that picture that I was giving you before. And they've also made it look cool by drawing pictures of mountains and trees and stuff on here. And so this was a recently updated diagram. And one of the things that you'll have for reading for this week is a overview of how they made this diagram and how they updated it from some of the previous diagrams that were being used, how they reconsidered how they were presenting some of these key stocks and flows, and in particular how they incorporated human activity into this, because human activity really shapes the hydrologic cycle in many parts of our Earth. Human activity like drawing groundwater out through wells, for example, has a big impact on the balance of the hydrologic cycle in lots of parts of the world. So that's the hydrologic cycle. That is an example of one of these systems and the ways that, in this case, materials are moving through the environment from one place to another. So now we're going to talk about the carbon cycle. And this is a really important system when we start to talk about climate change, which is going to be a big part of our course here. So the carbon cycle is a system that moves carbon around through our Earth. And the carbon cycle is also very complex, but we can start with the simplest sort of fast loop of the carbon cycle. The part where the most carbon is circulating over a short period of time within our carbon cycle. And that is between the atmosphere and the biosphere. So we've got a stock of carbon in our atmosphere, largely in the form of carbon dioxide. So, carbon atom with 2 oxygens attached to it, carbon dioxide. We got a bunch of that in our atmosphere. There's also some other carbon-based gases like methane that are up there too. So then we've got a flow of that carbon into the biosphere through photosynthesis. So I've got the biosphere broken down into animals and plants for this diagram because they're functioning differently in terms of their interactions with the rest of the carbon cycle. So plants engage in photosynthesis. They take in carbon dioxide from the atmosphere and they transform that into various more complex carbon-based molecules that help them to store the sun's energy. So they are pulling in energy from the sun and storing it in carbon-based molecules, and they're getting the carbon from that CO2 in the atmosphere. So they're building up now a stock of carbon in the bodies of those plants in the form of all of the carbon-based molecules that those plants are creating through photosynthesis. Then animals come along and eat the plants. So we have consumption as a flow from the substock that's in plants into animals. So animals like ourselves are also mostly made out of carbon-based molecules. So we take those on from plants and we break them down to release that energy that plants had stored there, and that's what gives us our energy. And in the process of doing that, we make carbon dioxide, and we breathe that carbon dioxide out. So we have respiration. So we're releasing that carbon dioxide back into the atmospheric stock. We're flowing it from the biosphere back into the atmosphere by breaking down those carbon-based molecules that we got from the plants, using the energy, breathing out the CO2 that is left. So we've got this nice little cycle from the atmosphere to plants to animals back to the atmosphere. And that circulates pretty fast, right? We're always eating stuff and always breathing out. Plants are constantly photosynthesizing and taking carbon in. So that is the simplest fast loop of the carbon cycle. But there are a lot of other places in our Earth where we can find carbon. So we can make our carbon cycle a little more complex here. So some of the new things that I've now added to our carbon cycle diagram. We've got the ocean. So there's a whole lot of carbon stored, dissolved in ocean water. And there are flows linking that to the atmosphere. So the ocean absorbs carbon from the atmosphere and then can outgas that carbon back into the atmosphere. So there's an exchange of carbon back and forth between the atmosphere and the ocean. Some of that carbon that's in the ocean ends up falling to the floor of the ocean, usually because it is incorporated into the bodies of ocean creatures. So carbon getting used to make, shells and things of ocean creatures from that oceanic carbon. They die, that sinks to the bottom through sedimentation. And then all of the stuff that builds up on the floor of the ocean gets compressed into rocks such as limestone that now contain a bunch of carbon in them. So that carbon has been moved from the ocean stock into this stock in the geosphere or lithosphere, in a rock form. But then that carbon can get released back into the atmosphere through volcanic activity. So if that sedimentary rock that's formed on the bottom of the ocean ends up getting forced into the earth through plate tectonics, which we'll talk about next week, it melts and it becomes part of a volcanic eruption. Those eruptions release CO2 into the atmosphere. So that carbon that had been stored in stone form now gets broken down and can return back into the atmosphere. We also have the fact that some of those plants, rather than getting eaten by animals, can get buried underground. And when they get buried, they take their carbon with them. And when they're buried, they eventually turn into fossil form. And in particular, they can turn into what we call fossil fuels, things like coal, oil, natural gas. So those fossil fuels sit down there under the earth until they either return through volcanic activity if the fossil carbon gets pushed into the earth through plate tectonics. It can go the same way as that limestone. Or if people come along and we mine or drill for those fossil fuels, we use them to power our cars, power our factories, power our power plants for electricity, etc. And so then the combustion of those fossil fuels gives off carbon dioxide and goes back into the stock in the atmosphere. And this human activity has really ramped up over the last century and a half or so. And it has dramatically changed the balance of the carbon cycle. This is a massive new flow that humans have added to this carbon cycle over a very recent portion of history. And so on this diagram, I just got a bunch of arrows, and all the arrows look the same. But of course, each of these flows is a different amount. Each of these flows is moving a different amount of carbon over the course of, say, a year. And so one of the things you're going to be doing in your homework exercise for this week is putting some numbers to some of this, looking at how much carbon is flowing from one stock to another in the carbon cycle, and how have those flows been changed by human activity. How have people altered this balance and increased some flows and decreased others, so that the amount of carbon found in the different stocks that make up our environment is changing. And so this leads us to be able to better understand the idea of carbon capture. So we're going to be talking a lot about climate change over the course of this class, and one of the solutions that people have suggested for climate change is carbon capture. If our problem is that we've got too much carbon flowing into our atmosphere, which is the underlying problem for climate change, is these enhanced human flows are putting too much carbon, principally in the form of carbon dioxide, into that atmospheric stock, and that upsets our global climate. So if we're putting too much carbon flowing into the atmosphere, could we correct that by creating a new flow out of the atmosphere to balance that out? Okay, so we've got a bigger flow into the atmosphere from burning fossil fuels. So then could we create a flow out of the atmosphere that maybe puts that carbon back underground where it came from, that will even it out and keep that atmospheric carbon stock in balance, even put it back the way it was before large-scale fossil fuel use became a thing 150 or so years ago. And there are a few different ways that people propose that we could do this. So one is through new technology, what we call carbon capture and storage. So we have some sort of a scrubber, and you see an example of one in the upper picture there on the slide. So the piece of technology that can absorb CO2 out of the atmosphere. And some of these are proposed to be put, essentially on the end of the smokestack that's producing the CO2. Others can just gather CO2 from the atmosphere in general. And they'll turn that CO2 from the atmosphere into a mineral form. So it's in a solid state, and then we can put that solid carbon-based minerals either down underground where they aren't going to affect the climate because they're no longer part of the atmosphere, or sometimes we can find industrial uses for them. Some of those carbon-based materials that they may produce in the course of carbon capture might be useful for manufacturing various sorts of products. As long as doing that doesn't put the carbon back out into the atmosphere, that could be a useful thing to do and could provide the money that's necessary to make that a economically profitable activity to do. Another way that we could remove carbon from the atmosphere is through so-called natural carbon sinks. So using existing natural processes, but amping them up. So that includes things like planting additional trees, because as the tree grows, it photosynthesizes, it's going to pull carbon out of the atmosphere. There are ways that we can increase the amount of carbon held in the soil. So there's a good bit of carbon in the form of organic materials in the soil. And there are different farming techniques, for example, that can increase the amount of carbon that gets stored in the soil and therefore not released back out into the atmosphere. There's also the possibility of ocean fertilization. So by adding certain fertilizers to the ocean, we increase the growth of phytoplankton, so the tiny little plant-like microorganisms that photosynthesize in the ocean. And if those things pull more carbon out of the atmosphere and then die and sink to the bottom of the ocean, that also creates a flow of carbon out of the atmosphere. So because these make use of existing natural processes, we sometimes call them natural carbon sinks, but the idea is that humans will increase the amount of this flow, will enhance this flow to offset all of the additional carbon that we've put into the atmosphere. So these are some of the things that you'll sometimes see proposed, and they're based on this systems thinking, this concern that we're creating an excessive flow of carbon into the atmosphere, so we'll balance it with a flow out of the atmosphere. Of course, there are potential risks and drawbacks to any plan like this. You might have first unplanned releases of that carbon. You pulled a bunch of carbon out of the atmosphere and maybe you're getting ready to pump it down into an old oil well to store it underground, and there's some sort of an accident and all that carbon goes back out into the atmosphere. And releasing that all at once could have serious effects on the local area, as well as undoing everything that you were doing by pulling it out of the atmosphere in the first place. There are issues with documentation and monitoring. How do we make sure that if somebody says, hey, I'm pulling all this carbon out of the atmosphere, that they're actually doing it, that they are accomplishing what they claim to be doing? So documenting and monitoring the operations of these schemes is a serious consideration. There are also potential ecological side effects. So you could plant a whole bunch of trees, but if you're planting, say, trees that aren't native to that area, if you're planting just row after row of the exact same trees and they're all going to be the same age, that's not necessarily good for any of the other organisms that might be living in that area. It may be effectively an ecological dead zone with just this one kind of tree growing there. That's not great for the overall ecology of the area. And then finally, any of these things require additional resources. You want to build this scrubber to take CO2 out of the atmosphere. That's going to require various sorts of resources to build those things. You want to plant a whole bunch of trees. Well, that requires land. It requires perhaps fertilizers and water and stuff to help those trees grow if they weren't growing there already on their own. So there are a lot of important considerations that we might want to think about before we jump on carbon capture as a solution. But the basic idea of it helps us to see this way of thinking of our Earth as a system and using this systems perspective on the carbon cycle. So for your lab assignment for this week, as I mentioned, you're going to be creating your own diagram of the carbon cycle. So you're going to be laying this out and then you're going to be putting numbers to it. And I don't want to scare you too much. The math that you have to do for this is just arithmetic. We're not getting deep into modeling the carbon cycle with calculus and stuff. Is just arithmetic, but there are some numbers because I do want you to see the scale of these different flows. Where are we seeing the most carbon moving from one place to another, and the size of the stocks that we have? Where in our Earth do we have the most carbon hanging out? And so to understand that, we got to put at least some basic numbers to it. So you're going to be using just some arithmetic to understand the workings of the carbon cycle, and that will allow you to evaluate whether the system is in balance, and then also to examine the impacts of human activity. As human activity changes some of these flows, what effect does that have on the overall carbon cycle? So that is your assignment, and I will be back next week.